So first of all, you all should be aware that the first assignment has been announced and the deadline is approaching quickly, right? So are you working on it? Have you finished it already? Not yet? No. Have you started working on it? Think about it. Okay. Well, thinking about it, you still have to produce code. Thinking about it alone is not going to be sufficient, but I'm also of the opinion that often thinking about the problem first is not a bad idea before you start slinging code. However, before that, also think about the data that you're going to get. So actually getting some images of the kind of shapes that you would like to generate for our Connect the Dots game. Where to get them and what they would look like is probably the most important thing, because that will steer your thinking then hopefully in more fruitful directions, as opposed to what you may envision. A lot of students, a lot of computer scientists, a lot of software developers, since they like to write code, I often feel that they start too quickly, because once you start with your favorite programming language, a new editor, often the exploration part is kind of limited, because you start writing for loops or a functional programming approach or something, and then that often it's easy to lose track of what the actual goal is and what the actual input and outputs are supposed to be. So if we do that for this particular domain, then let's think about what kind of images we would like to use as inputs. So any ideas? Okay, whether it's RGB or grayscale is really no big deal, right? Because if I have RGB, I can easily go to grayscale. So I don't think the color space is so important. But if we look at my nephew, because the whole assignment, of course, is only to make my life easier, right? So that my nephews are going to have some games to play and they don't bug me all the time then, right? So they like dinosaurs. So if we just type in dinosaurs into image search space, then we get something like that, right? So what about that image? On the difficulty, if you were to gauge it from difficulty from 0, anybody can program it, to 10. Only Jeff Dean from Google would probably be able to program it. Then how would you rate this?
Personally, in between 5.
Oh, well, obviously, if 0 and 10 is the range, then somewhere in between it would be, right?
Ideal, yeah.
So you think it's a 5, okay? I think it's actually quite a bit harder than that, because if you think about algorithms that you could apply, right, in order to get the first point is, clearly if you get that image, right, the resulting connected dots should draw the dragon, the dinosaur, right? So, first thing you need to know is which pixels belong to the dinosaur, right? Which pixels do not belong to the dinosaur, right?
Are we allowed to do any image pre-processing? Or
Yeah,
should
sure.
the system be allowed only any kind of image? Because if we feed
The system should work with any kind of image. It shouldn't crash because you send one image, but the quality of the output will probably be different.
Because I feel like the third is very different from the first.
The third is very different from the first because
I feel like edge detection, for example, would be easier.
in here,
Yeah.
really?
Because everything is the background completely black or?
No, okay, there's trees here.
There's trees. Okay.
Actually, there's lots of vertical lines that
Okay.
you may trigger there. So, I would say that as far as edge detection is concerned, the second image here is much easier than the third, and a little bit easier than the first, right? Because it at least sort of he stands out like that. Okay. And then, but that's the kind of the key point, right? We cannot do any processing until we sort of have an object, and then we can find the contour, and then we can apply algorithms for trying to reduce the size of the length of the contour. So instead, how about these images? And I think Google image search was very kind to me because it put it in just the right order, right?
Oh, yeah.
Without me doing anything. So these ones would be vastly easier, right? They will be much easier to process. In fact, I think we could just look at these kind of images, right? And that will be sufficient. So maybe we start with those, and then we see how far we can push the algorithm. Now, I'm not sure about the copyright of these images, of course, but the same thing you can do with your generative AI algorithm, right? If we look for clip art images of dinosaurs, I think that would be the best kind of input images. And we would think that this we can definitely convert into a connected dot. Right? And then we can look at other approaches for the more complex images. So maybe here we want to be able to process all images, but our first sort of cut at the algorithm, we want to look at these kind of images. And then here, if we want to process these kind of images, that's why I said in the description, we probably need to apply something like Midas or another deep learning network in order to do foreground background segmentation for us. But there are several that you can easily find in the description, and there's PyTorch implementations that you can just download and run. And MEDAS actually works quite well. I haven't tried it with the dinosaur images yet, but it's pretty nice, giving you a depth image, and then you would simply filter out anything that's not in the foreground, anything that's not the remote depth of the camera. Anything that has depth label that is too far backwards, we just ignore that and think that's not part of the background. Then we may get kind of clip art images. But the first part, that's kind of the pre-processing step, right? And then the second step is working on the outline and simplifying the outline and some of the internal features. And I think if you look and generate dinosaur images from clip art or other kind of images, what else do little boys like? Cars, fast cars. Something like that. You can get some ideas of the processing that you need to do in order to simplify the contour. Now, fine contour is already implemented in OpenCV, and it's a standard algorithm. It chains the pixels, the edge pixels together in a continuous outline. Then any ideas for how you would want to simplify it? See if they're online. Or actually, you guys can do that for the next 15 minutes. Implement, load an image, and then just run the, or load a clip art image, so it's easy to segment. And then run fine contour, and then look what the contour actually looks like, what data you actually get from the contour.
So the contour is the actual outline of the
Outline of the object, yes, it should be the outline of the object.
So we can just like on position, like 1, 5, 1, 2, 3, 4, 5, and then pick up those pixels that on the line.
It'll be better. So find the contour first, then we can discuss algorithms for simplifying. But yes, one approach would be if you have a contour of 1,000 pixels, and that's too many to paint, right? So you just want 20, then you just take every, what would that be, every 20th, every 50th pixel. Every 50th point in your contour. That would definitely reduce it from 1,000 to 20, but you'll see. And I will implement the same, but you should definitely try and do that yourself first. And I guess I need some generative AI, so let's try how that works. Ah, last time it was too slow. I hope it's not slow this time. Hey, how come? Oh, what is this? What is it asking me now about GPT-4?
Later on the right side.
What?
Click the right side. It's later.
This one?
Yeah, this one.
Later.
Yeah.
Okay.
Or you will just pop up the GPT-4 message.
Okay. GPT-4 message. What GPT-4 message?
Advertisement or something.
Okay. Yeah, I need more advertising in my life. So how come? I really have bad luck running this. Yeah, okay, let's see if DALL-E 3 can get it done. But can you just tell me what am I doing wrong here? How come this? Do I have to type it in Chinese? Shouldn't be, right?
Yeah.
But here it just. It's just weird.
No response.
No, nothing here. Here's the Taipei 101 skyline. This is better then. So maybe I should have gotten rid of the skyline because otherwise I have. It's weird. Like they used to. My other Windows computer, it just keeps keeps creating images. I just type it. Actually, even if I just type in the search bar, it comes up with images. But now it's strange. Okay, I give up. Just copy this one. Where do I have copy image? This is edit, right?
Yes.
Let me try edit.
The top left button is the save image.
Okay. Oh, and it's very tiny. 85 by 115. I cannot even. Oh. Save image.
The second one.
This one is edit, right?
No, this is saved as a new file. So
Okay.
just
And where do I have settings here? See? No.
please copy.
Copy, paste. Tools.
You want to
Change the language.
change the language.
So it should be settings.
The third one from the right. Yeah. Yes. Let me do for you.
Yeah.
Okay, setting language. Efficiency. Source language. Tool.
I think it should be there.
Yeah. Just
Wait, go back to the general there.
window.
No, the first one.
The first one.
This is not any of the languages. No.
It's a cursor setting.
Okay.
Would you like to paint or
Yeah, yeah, yeah.
maybe just use the pen
Windows Paint.
Yeah,
Okay.
default software.
Okay. Okay. Thought it was here before. I've done it before once successfully, but
I'll double check.
it's very powerful software. A little bit nicer than the GIMP. Oh, maybe I can work it out. And what's image 1? Anyway, now I can crop.
Everything works?
I just use it with the Chinese interface now.
I just found out the steps to settings is the one we just click. Yeah,
Okay,
setting
and then
general. General means
general, okay.
yes, this one.
This one is
And then
general, and then
we will find the language option. No, there's no
liar! That's ChatGPT help for you. General, no. But I thought so too. I thought it was here somewhere. And then there was actually a long list of languages you could select. But
maybe others, the second one here.
others?
Yeah.
Hmm.
Yeah.
Okay, never mind. I think I can crop without that. second. Let's have a look at the image. Okay. detector, it can look like that or more, but a simple Sobel in X and Y is going to give you similar results. So the actual edge detection component is not going to be a problem, I don't think. So yes, you can use, or I think it says in the assignment specs that you can use OpenCV or other libraries. You just have to say which libraries you're using.
It's not good as expected.
It's
Just
always
call the find contours method and just find those pixels.
right. Yes.
May not just so the dots will be
There will be parts of the contour, yeah. And actually, it's not bad if you were to draw those in. And one thing is the general outline of the dinosaur should show up as well. So you need to check your threshold values.
okay. Because the contours must be found in a grayscale that image defined by the OpenCV. Yeah.
Actually, it's not just a grayscale image; it's a binary image, basically.
Oh, binary, yeah.
That you need to look for. So try and lower this threshold value and then see what you get. And actually show it to him as well. Come over here, you can have a look and see what that will look like. And as you can see now here, the legs are very nice, right? The nose, the eye, the mouth are all pretty cool, but the body is missing. And so in theory and in practice, if we have an image like that, then I would probably get rid of all the white connected shapes first, right? Because then whatever is left should be the shape of the dinosaur. So you could do that, but for now, just change the threshold to and then see what you get and how many contours.
Oh.
Oh yeah.
Right?
Oh, it's perfect. Wow. So what was the value of the threshold?
Okay, but of course that depends on the image, right? Right now we use 64, right? I think with a constant background like that, you should be able to find pretty good. But I'm surprised how come it doesn't find the eyes in. Because it finds the contour, it finds the outline of this, so the eyes will be inside now, and then it won't register those.
Yeah, for the green arm.
The outline only on this, yeah. But we have to, in order to make it a really great connected dot, right? This will be fine for the connected dot thing, but to make it a great one, the eye would actually be on the page, right? If you look at the puzzles. Hey, what is this? No, this is dot connect instead of connect the dot. Images. Yeah, like this, right? If you just have the outline here, then it's not going to be as funny as having the inside here painted in on the page, right? So we could apply this recursively once you have everything inside of the dinosaur shape, right? You can then think about getting rid of that border and then look for regions inside of that shape that you can draw. And if they're a certain size or certain
But isn't that problem, like here it's just some, maybe some other dinosaurs, more intricate portraits?
yeah. So then you would have to look at the, I think that you would get out of controlling the threshold for the edge detection to determine what you see as different pixels, and also the length of the contour. If it's only like 4 or 5 pixels, then it's probably not worth to have a separate feature for that. But that would be the additional step. Let's start with this shape first. And right now, you have a threshold value here, right? So you have to be aware of the fact that now you have a parameter that you need to tune for your algorithm. So at the same time, you may think about ways in which you can automate setting this particular parameter there. Right? And how would you go about doing that?
Every time we apply the threshold to calculate the number of units.
Yeah.
And that's why there's few pixels.
Right. In fact, I think it'd probably be easier for this kind of image, right? You simply want to, if this is white, right? If this is white, you can simply lower this threshold until the number of contours returned is 1, right? Then that would just be everything as one contour. That may run into problems, but that would certainly be able to automate. You could also look at the difference between, once you detect a contour, you can look for the difference between the pixels that you found as part of the contour and the surrounding area. And and see what, how much difference there is, and see if you can bump that up a little bit, for example, like take some statistics from that particular threshold, and in order to select the threshold, right? So, because right now you have, after you run the algorithm, let's say you start with 127 as your guess, right? The idea is if there is some algorithm that we can apply to find a better threshold. Now, you have a threshold of 127, right? So then, maybe if we think about it like a decision tree, right? Then, when would that threshold be okay?
The number of pixels
It wouldn't be rising because this is our first time that we run it, so
okay. So we don't know.
we don't know how many pixels there should be in the outline, right? But if I have one outline with greater than 100 pixels, right? Then I would think that probably is the right shape, right? The other question, so no. Then we have to determine what's the what is the what thing which direction. First we determine which direction we want to move this threshold, right? So when do we want to go up and when do we want to go down? By up and down, I mean include more pixels, and here the other one would be reduce the number of pixels.
Number of pixels in the image.
No, in the contour.
So we want to increase the contour when it's not enough. It's shorter than we.
Right. Yes. Yeah. So let's say I only have 4 pixels here, then I want to increase that, right? Because at that point, if I set my threshold, actually you can try that. Set the threshold to 0, and then print out the contour. Instead of 64, right? We were at 127. Now we changed it to 64. Now it's better. So let's try 0. I think it's because it doesn't include the 0. Like, and ideally now the whole picture. Can you plot the threshold? You can just do CD image show binary. You don't need to copy it and wait until the end. So just copy this line and then just plot the binary show. There should be another. Oh, because you have the same name, you have to give it different names. So one has to be binary and the other one has to be. Yeah. Okay, so so it doesn't include 0. I actually wanted it to go all the entire image, right? But the threshold doesn't even allow you to do that. corners of the image, right? Those are the only edge points that it would have. Oh, okay, yeah. Because I'm not sure what it. Yeah. So, but it still doesn't accept all of that, right? So.
Zero means the center value for the value to separate two parts.
No. This is the limits, lower limit and higher limit that you set. And then if you want to set it to 1 or 0, I think that's how the threshold works.
From 0 to 255 is all the pixels.
Should be all pixels, but I think it doesn't actually do that. Maybe because. So anyway, yeah, if our contour is too small, we want to increase the threshold so that we get more pixels. If our contour is too big, then we don't actually know, right? We wouldn't know what the correct length for the contour is. So there probably is no there's no way in which we want to reduce the number of pixels, right? So I think we only want to do this, and if it's not that, then instead of decreasing it, then we just say that's okay. Then you can run that iteratively, changing your threshold, or you can take it in jumps, like I try 127, you can do a binary search like 127 and 64. If that's better, then I go to 96. If it's not enough, then I go to 32. That kind of idea. Or you can just go in steps of one that would run fast enough and wouldn't be a big problem. So think about the threshold, and then now set it to 64 and actually see what the contour looks like. So you want to check if there are any contours. And then also print out the length of contour 0 to see how many pixels are actually in there. So print the contours. No length, just print the contours themselves. Okay, and there's more than that. So there's 2 pixels. Oh. So go to the there's so it's a sequence of one-dimensional numpy arrays. That's why the length would be 1. So you need to print contours 0.shape or yeah, in all non-paragraphs, they should repeat that. one row, one column, two. So that's just a single point. But now if you print lane contours, then how many do you get?
The first one to
Single pixel. Yeah. So you want to print the size of all of them now. Like for C in contours, print C dot shape. Now you need to do that as a loop. But you can also print contours dot shape. But that may be a list. I'm not sure if that's a numpy array. Yeah. So that's a tuple.
so there's a tuple of
Correct. Yes. And
but we only need the first one.
not sure. I don't think so. I think we need the longest one because you have one contour which has size 1 now. Print out contour dot shape and maybe a count too. So
Okay, there are 7.
yeah, and the longest one is 450
I guess
pixels.
that's the one is the largest one.
Yeah, I don't think they're sorted.
Yeah. So that's 7th one.
Yeah. So I think when you want to process it, you want to use the longest contour first. And that's okay, that makes sense. Then you can try and play with your threshold parameter, or you can try and adjust it automatically. And once you have the contours, then any ideas for how to improve our outline? Like right now, 450 pixel takes you 10 seconds to draw a line between the 2 pixels, right? That's already over an hour and a half, approximately. 3,600 seconds is 1 hour. Be an hour and something over an hour. Painting your picture, that won't be a lot of fun, I don't think. So now you want to look at the data that you actually get for the contours, but what you get will be the I'm not sure, I think it's the y-x coordinates of the pixels that make out the shape. And then what? Then how do we simplify it to like 20 or 30?
Select 1 per 10 pixels.
Select 1 per 10 pixels, yeah. That will be the simplest idea. But I don't think that that will be very efficient, very nice. Because let's say you have a shape like this. An airplane, right? From the top down, airplane from the top down would look something like that.
Okay, the distance between the 2 pixels are
Now your contours is, because this is not going to be aligned exactly with straight lines, so we're not sure what your algorithm is going to find. But let's say I have some pixels here, and then here there's a little bit of noise with camouflage and everything, so then I get a lot of pixels there, right? And then some fewer here, and then one there, for example. If I now just take every 20th pixel, then on here that may work out, right? Because I only take every 4th pixel or 5th pixel, right? On the wing, that's okay because I have 1, 2, 3, 4, 5, right? Then I go to here, and then I have from here, I would do 1, 2, 3, 4, 5. Well, that's already a huge cut, right? And then from here, 1, 2, 3, 4, 5 would be there. So I will make another huge cut. Right? So I don't think just picking the X pixel is going to work well. Instead, we need to look at
maximum distance.
Maximum distance. So that's still, I think that has a problem if you have a shape like this, where the pixels are actually close together, but the shape is kind of important because you're trying to do a screw or something like that, right? In that case, you would say, oh, we can just replace that with a single straight line. I think that is also a little bit too naive. But it's better than just every nth pixel. No, I think we really need to worry about the error that we introduce. Basically, we want to remove pixels, right? Clear? So if I want to remove pixels, then I have a pixel that is before and a pixel behind me, basically, right? Like I'll be between 2 pixels. And then I think what I would implement would be to look at how much, if I now follow the shape, right? Then I would get this area that is added or changed, right? It'll be either added or reduced, taken away from the actual shape that I'm generating. So here, if this is the inside of my shape, right? Then here I would cut out some part. Or if the pixel is here, then I would add some part to it, right? And so then one heuristic that I think would work for reducing the shape would be to simply look at the area of error that we introduce. Right? If I go from here to there, then I introduce this much error into my outline, basically. And if the pixel is here, for example, then the error that I introduce will be much less. Right? Only that tiny little sliver.
So let's do some errors there.
So then, for 400, you can easily iterate through, right? And then simply say, if I remove this pixel, how much is the area going to change due to I'm making that modification. Then you take the one, you take the one that reduces, that has the minimum error that is added. And I think that should work.
Can you explain again what area are we considering? Like, what is the root?
I have a contour, right? 3 points.
All right.
And those 3 points will define a triangle, basically.
Yeah.
Right? And right now, if this is inside, right? If this is my contour, then the shape is going to do this.
Okay.
Right? If I now replace that with a straight line, which means I remove this one,
yeah.
then the difference between the previous contour that I had and the previous contour is all of this, like that, right? Wherever it goes.
Okay.
And now the new one goes from here to there. So the difference between those two contours is going to be the area of this triangle, right? And that's it. So that's what I would use as a heuristic for determining which, and actually that's what a lot of the contour algorithms already use. Like, so I'm pretty sure this will work. Now, there are, and then basically your goal would be to find from, how many pixels do we have? 450?
Yes.
From 450 to 20 pixels, right? Which ones are the, which ones are the 20 pixels that, if I keep, most accurately correspond to the shape, the original shape that I have. Now here we're basically, this would be considered a greedy algorithm, right? Because at every loop for our algorithm, we pick the one that at our current situation has the best error, or that minimizes the error, or improves our performance the most. Right? Now, greedy algorithms don't always work, because if I'm here and I'm doing this in the navigation domain, right? I'm here in this position, and there the wall is blocked off, and I want to leave through the door, right? Then, I'm in this position here. Where do I go? Well, direction of the wall, right? So best I can do is here. Then I keep going, and I keep making greedy choices, and actually, I end up in a dead end there, then I have to backtrack and figure out. So, using a greedy algorithm, we cannot guarantee that this shape actually is going to be the best 20 points that we can find. So instead, it will be better, basically computationally our problem is find the 20 points that best correspond the shape that that we were trying to model, right? But that's actually, there's a couple of problems with the way that we formulate that problem. Because if I make this assumption here, right, if I apply this approach, then I think it'll actually work, but it's not quite clear. In this case, the shape would be mostly defined by the area that our points span, right? But I'm not sure if that's true for all shapes. Probably there are some shape some images um, where the area may not be the most crucial feature. Like, you could also do the same thing and you could say, well, actually, I have 3 points, right? And I'm trying to reduce those as much as possible. But clearly, what I should be doing is, if I go from here to there, right? Now, here I have an angle of alpha 1, right? Between the previous line segment and the next one, and then the next one. Here I will have alpha 2. And then you could argue that now I'm changing from alpha 1 to alpha 2. Right? That's a different angle now. And I want to take out those points where the angle change is minimized. Now, in some situations, this will return the same point that we want to reduce, right? But in other areas, it would be so it would be in cases where the shape is more important than the area of the image. So I think that would be mainly for small contours, small parts of the image, small areas of the image where the shape is really important. So what kind of things could that be? Let's say probably it would be things like that's why you need to be careful with your topics too. Different topics will be different. Let's say you're doing something with a dollar sign, right? And that's part of the overall shape that you're interested in, or musical key. I don't actually know about music, but I think it's like something. No, this is terrible. Whatever any one of you is a musician? You know how to draw it? Okay, then draw the thing. Yeah. Okay. Yeah, I did sports. I didn't do much music, so it's horrible. It's really embarrassing. So if I want to do that, then maybe from here to there, I have very small change in the area, but it's actually really important to the shape. Otherwise, it's not a musical key at all anymore. Right? So I can see that area is for the dinosaur pictures. I think area is going to work the best, right? If you have very intricate features, then I think that are not sort of spanning out an area in your image, then I think the angle may be more important. So it's not just a single, but we focus on one. Of course, if you are a PhD, trying to get your PhD in computer vision, then now you would sit there, talk to your professor and say, actually, maybe I can have an algorithm that takes 50% of the score is based on the area, 50% is based on the angles. And then you can mix and match for as much as you want. And this is kind of the story of artificial intelligence research in a sense too, and lots of other algorithms. So the initial idea, right, we want to reduce the contours by taking out one, right? That is like 80% of the performance. That's one guy that came up with a really clever idea. And then there's 30 years of research to push it from 80% to 92%. And extend the number of domains where it's applicable and things like that. So that's happened a lot in AI and planning research. However, I would like to point out that here, our greedy algorithm is not going to be optimal, right? Because if we decide to keep a point and then we reduce one, then by reducing two of them, I may be able to do a better job with minimizing the loss of the area, right? But why don't we do that? Because I could also say, oh, I know how to calculate the optimal algorithm, right? I have 450 points, I pick 20 of them, then I calculate the area, then I pick a different 20, calculate the area, pick a different 20, calculate the area, and then I just pick the one that maximizes the area size. Would that work?
I have a feeling it would. I'm trying to think of examples where it can't.
I also think it would work. Unfortunately, none of us are going to be around to find out because what's the complexity of this algorithm? First point I have, how many choices? 450, yeah. Then the next point I have, how many choices? 449, right? 448, so on and so forth, 20 times, right? Which is, I'm not sure, is that how you show it in Taiwan? Choose 450, 20, right? So choose 20 points out of 450, which is equal to 450 factorial divided by 20 factorial multiplied by 430 factorial, right? And 450 factorial is an enormous number, right? So the universe is long dead before we get one dinosaur calculated. So that's why I think that's why I propose the greedy approach in this case. And the hope is that by doing that iteratively, we end up with a shape that is sort of reasonable, even though it may not be optimal.
Because the algorithm eliminate or remove pixels values. Like in the first I eliminate 10 pixels, and the second one I also.
The greedy algorithm would remove one pixel.
Okay, only remove one pixel.
Yeah. And that should be fast enough. Like you can run thousands of loops on a computer easily enough, right? That's not going to kill your performance. if that is an issue, then you could implement, because from the problem it's clear that if this is our dinosaur, right, you can probably fiddle around with this area here and this area here and this area here pretty much independently, right? So for this particular algorithm, the greedy algorithm would remove one at a time, right? If you want to do this faster, then certainly you could just run in a loop and remove all the pixels that are below some threshold, right? And then say, okay, those are too small to make any difference. And then you run again another loop. So then you may remove 20 pixels in the first loop, and then 10, and then 23, and eventually you have less pixels below your threshold and you stop iterating. That would also work. I would start with the greedy algorithm. I would change to the other version by if the runtime really is too long. But I doubt it very much. I think it'll run just fine on thousands of pixels of contours. It's not going to be a problem. You can also then try and come up with some more clever algorithms. So for example, here, you can kind of take the shape into consideration, try and look at for the density, like how many pixel points are in this area, right? And if there's lots of pixel points in this area, then you start doing it slowly. And if there's a few pixel points, then you use a different threshold, right? Or you reduce the first pixel that's below your threshold, you use that as a new threshold, so that you go through the image and you say, okay, if the area is less than 0.7 pixel units, right? With pixel units squared, basically, however big you think the pixels are, doesn't really matter. If it's below the threshold, then I cut that pixel. Now that pixel that was, my threshold is 10 pixel units squared, right? But the one that I cut out, it actually had 3 pixel units squared. Then I use that for threshold. I say, okay, I already decided that I'm going to take out that 1 pixel unit here. Now I'm just going to go through the rest of the chain and see how many are with that threshold or lower. And then I keep reducing those. All kind. This then has very small impact on the actual performance and the actual output image that you get. But there are more clever ideas that you can come up with that you can explore in this assignment. So in this assignment too, you want to focus on reducing the size of the contour. That's kind of the most fun part. The thresholding and finding the contour is a standardized algorithm. There's not much you can do for improving on that. And then I think that should be fun. Yeah. But I suppose you start with the number of comic images or clip art images that you can either download from the internet or use generative AI to generate them. And start with clip art images because those are easier to deal with than the natural scenes that are generated by that we can find. And then think about finding the contours, finding the right set of contour that you want to optimize, and then pick your algorithm for reducing the number of points in the contours. Let me just calculate that quickly. Find the image.
Let me share the notebook. And here, start with the green channel. And then actually, if I look at that image and the image that we have here, that you have, if we look at the contours that you have, if you can just show it to us again. We had it before, now you have, now you just show all the points. Yeah. Just every step, yeah. Okay. Actually, it didn't work too badly on the dinosaur, but I think for more complex shapes. So these are the shapes. Also, you can see my image there of the 5K 101. I did a crappy job with the photo editing because that could be improved, but there's also some artifacts due to the JPEG
which is why you got those blocks, right? When you ran on everything, then you could see that the lines were all horizontal and vertical, but that's due to the 8x8 filtering of the JPEG. I think it does 8x8, I'm not sure what kind of block size it uses. And so that introduced particular artifacts for particular blocks, which is why your shape looked like a staircase. So I think probably it would be a good idea to get rid of the noise that you have in the image first by blurring it, at least run a small blur pass over the image. Because we really only want strong, very strong edges, so then getting rid of individual pixels that hang in the middle of nowhere, I think will probably work quite maybe advantageous. Yeah. So for looking at that image, I would add a simple Gaussian blur over the image.
So apply the filter first.
Right, yeah. Maybe. That is interesting. Oh, okay. So the sample code in the OpenCV directory also already includes the blur.
So we don't need to apply it.
Oh, you have to. This is the sample code that they recommend. So they also blur the image first. And the size of the blurring kernel depends sort of on the size of the image that you have. If it's a 320 by 240 image, then probably blurring 3 by 3 is enough. If it's a 4K image, then you want to use a larger blur algorithm. I mean blur window. You want to blur it over a larger region. Then I can apply any kind of edge detector, including just the Sobel edge detector or Canny edge detection, which is an enhanced version of the Sobel. And here I need to look and see what kind of thresholds I want for the Canny edge detector. Then that I would have to guess. 60, 120. And then let's have a look at that Canny image. So now let's see here. Yeah, I think that should work. Yeah, you also, with fine contours, you also have to read the documentation or the chain approximation algorithm. You can actually select one. Like there's a bunch of options. Simple usually works well enough, but the other ones use more elaborate ways to create the contour. And then we can draw the contours. And then let's see what I get. It's my image of the Taipei 101. Okay, I thought I... scalar value for argument color. Huh. Well, I want to draw is drawing them, so why? So what do we want? Oops. Color, so color of the contours. Color is not numeric. So these are the contours that I get. Unfortunately, I can get a tuple, but not. It's weird. C for C in colors I. Scalar value for argument color. Int. No. Why does it not like that? And here with different colors, just randomly assigned colors. So you can see quite a lot of segments I have here. I can contours max of sort it. And contours 0 to 5. How do you do reversed sort in Python? Come on, it can't be right. So here I have some statistics for this Taipei 101 image. Total number of contours, 253. The longest one is 880 pixels, then 680, then 426, then 317, then 305. One thing that we could be doing is plt.figure. Draw a histogram of the size of the contours. And then you can see it's distributed like that, which is not unusual, but you can see we have a huge number of small contours, right? 200, more than 200 contours are less than 200 pixels. And then we have the long ones that we had already, 800, 600, 400, and greater than. So looking at that picture, right, I may conclude that I ignore all the contours that are 4 pixels or less, right? So that would make my job easier. And most histograms, you often find this kind of inflection point where you have a lot at one side and then it drops off dramatically, and you can sort of identify which area size contours are of interest. So then here we have So then I can play around with this and only draw the contours that are so don't pass in the hierarchy. Okay, let's just plot that up to 2. Okay, so here. So here I only have the long contours, and you can see I have a lot of noise here, so that those contours are pretty long and convoluted. And some of the ones down here are very nice. That would be good enough. I think the contours then I have to greater than 100. So now you can see with our edge detection, with the candy edge detector, when I run it through there, right, I get a lot of contours that are sort of separated out. That's actually not incorrect in the sense that in the original image, the individual floors are actually two separate rectangles, right? But in my case, I would like to merge those. So I would probably apply a morphological operator dilation in order to make longer chains of edge pixels together, right? So that would be, and then eroding them afterwards. So you can run dilation followed by erosion in order to get longer chains there. And that also shows in your algorithm, you also need to think about that, like how to merge different contours. And if they're close together, the pixels that we add to the shape, they may not all belong to just a single contour. They may have split it up into multiple contours. So somehow you have to deal with that problem as well. And then the outline here, this is all pretty nice. And here we have some noise, so there's lots of pixels in this area, but we cover a very small region. So the density of the points is going to be very big in there. But I think by just looking at the area, those we can filter out. Okay, good. Then that's it for our investigations today. I think the type A 101 is quite a complex shape. Hopefully you'll do better with the dinosaur images. Otherwise, you need to simplify those some more. So also the resolution of the picture was quite high, so that's why we got a lot of fine details in the image. Probably want to resize it to a smaller image first before you apply your processing there. Or generate images that are smaller to begin with.